Hello and welcome again to my Physics Online video lecture series. Today's video we're starting in on a new set of topics, which is electrodynamics at this point, or the very beginnings of electrodynamics. And the first topic in that is electrical current. So what is electrical current and how do we measure it and so on? Electrical current is often represented by the letter I. We often use a capital I to represent current in physics. So electrical current is defined as follows. If we're using an I to represent current, then I, on average, is mathematically delta Q over delta T, where delta Q is charge. So you could think of this as charge flow rate. And what it is it's basically how much charge per unit time passing through a given cross section within some region of space, like a wire or whatever. And it has units of amps. So the unit of amp or ampere is represented by an A. 1 amp is 1 coulomb per second. All right, so we've now defined what the unit is. Now, as it turns out, the amp is sometimes considered the more fundamental unit. It is definable aside from charges in terms of how much force a pair of very long, very straight wires will apply to each other while current is flowing through each of them. Essentially, if you have an amp of current flowing through the two wires, then they will apply essentially like 10 to the minus 7 newtons on each other of force per meter length. So that is current in bulk. A lot of the times it is analogized to fluid flows, and essentially your charges moving are kind of like the fluid, the water, or whatever you have flowing through a vessel. And so the more fluid flow you have per unit time, the higher your flow rate, the more current that would be analogous to. Now, current is a conserved quantity, or charge is a conserved quantity, so current ends up being a conserved quantity. And so what that essentially means is that if you have a junction like this, where I have current going into the junction, and then I have a split, so maybe I have like two currents going in, we'll call this I1 and I2, and then I have three currents coming out like this, I3, I4, and I5, then this conservation law would say that I1 plus I2 is I3 plus I4 plus I5. And that's this idea is what's sometimes called the Kirchhoff junction rule, which we will treat a bit more in the next set of these lectures. It's usually in the next chapter after the one that introduces current, if you're following along in a textbook. All right, some other stuff to know about current. The direction of the current. So direction follows positive charges, and it is opposite direction of negative charges. All right, so that essentially means for current direction, if I have a wire like this, and I've really blown my wire up a lot, and now I have, let's say, a bunch of positive charges that are drifting this way in the wire, like so. And then I have a bunch of negative charges. Let's do the negative charges maybe in purple, just for the fun of it, that are also drifting along in the wire, but in the opposite direction like this. Then the current direction will be in the direction that the positive charges are moving. So my current I would actually be in this direction. And that is true even though the negative charges are the actual existing electrons are moving around in this wire. The positive charges are electron holes. They're basically virtual particles that are sort of like left behind when an electron is removed from an atom. Where's the positive charge coming from? Well, you still have the nucleus of the atom, and it has some plus charge, and then you have your electron cloud, which has some minus charge, and if you've pulled one electron off of that cloud, you're left over with a net of +1. And so if you move an electron from one atom to the next, to the next, to the next, then that hole that you've taken the electron out of is kind of moving in the opposite direction. But that hole is in the direction of the current. And there will be more explanation for why that is in a future discussion. I think we'll spend a little bit of time doing some quick examples to close out this video. Our first example is fairly straightforward. We want to know how much current is present if you have 6.02 millicoulombs worth of charge moving through a given section of wire in 3.01 seconds. So the current is given by the charge divided by the time, and the charge in this case is 6.02 millicoulombs. The time is 3.01 milliseconds. The millis actually can cancel, so you don't have to convert the units like this, but if you wanted to, for the sake of consistency, convert units, you'd have 10 to the minus 3 coulombs per millicoulomb, and you'd have 10 to the minus 3 seconds per millisecond. And so, of course, your 10 to the minus 3s are also canceling. What you end up with when you plug all this into your calculator is 2.00 coulombs per second, or 2.00 amps. Now, the follow-up question that goes with that is how many electrons or electron holes per second is this current equivalent to? And so the answer is, again, given that I is equal to delta Q over delta T, this is equal to number of particles per time times charge of each particle. So that means that the number of electrons per time would be equal to the current divided by the charge of an electron. And so you have 2 amps divided by 1.602 times 10 to the minus 19 coulombs. If you plug all that into your calculator, what you will get is about 1.248439, etc., times 10 to the 19. So let's round that to to the 3 significant figures that we have to work with, your number per unit time would be 1.25 times 10 to the 19 particles. And that's it. So hopefully you've learned a bit from all this, and thanks for tuning in.